Our third speaker is Nisa Bostanci. She's a second-year PhD student at ETH Zurich with Onur Mutlu. She's interested in security and DRAM and hardware-software co-design. And we'll hear her paper on CoMeT and another different way of tracking aggressor rows, I suspect.
Yes, thanks for the introduction. Hello, everyone. My name is Nisa, and today I'll present our work, CoMeT, continuous sketch-based row tracking to mitigate RowHammer at low cost. Let's start with an executive summary. As DRAM becomes more vulnerable to read disturbance, existing RowHammer mitigation techniques either prevent bit flips at low performance cost but with high area overheads, or at low area cost but with prohibitively large performance and energy overheads. And our goal is to prevent RowHammer bit flips with low area, performance, and energy overheads in highly RowHammer vulnerable DRAM-based systems. Our key idea is to use low-cost and scalable hash-based counters to accurately track DRAM row activations. To this end, we propose CoMeT, which tracks most DRAM rows with scalable hash-based counters by employing the continuous sketch technique to achieve a low area cost, and tracks only a small set of DRAM rows that are activated many times with highly accurate per DRAM row activation counters to reduce the performance penalties. Our comprehensive evaluations show that CoMeT achieves a good trade-off between area, performance, and energy costs by incurring significantly less area overhead and outperforming the state-of-the-art mitigation techniques. CoMeT is open source and artifact evaluated, and you can check our source code and all scripts from this link. This is the outline of my talk. Let's continue with the background and the problem. So today's DRAM chips are vulnerable to read disturbance by repeatedly opening and closing or activating and precharging the same DRAM row results in bit flips in nearby DRAM cells, which we call RowHammer bit flips. And we refer the activated DRAM row as the aggressor row and affected DRAM rows as the victim rows. And we call the minimum number of activations that cause the bit flip the RowHammer threshold. DRAM chips are becoming more and more vulnerable to read disturbance today. And read disturbance bit flips occur at much lower activation counts. And these two recent works show that the RowHammer threshold has reduced more than 2 orders of magnitude in less than a decade. So the mitigation techniques against read disturbance attacks need to be effective and efficient for highly vulnerable DRAM-based systems. One approach to mitigate RowHammer bit flips is to preventively refresh potential victim rows, but to do so requires tracking DRAM row activation counts of aggressor rows to identify potential victims. Let's look at an overview of preventive refresh-based mitigation techniques. The first approach is to allocate one activation counter per DRAM row. And since these counters are pretty accurate, 100% accurate, the mitigations based on this approach incurs very low performance and energy cost because they preventively refresh when it's absolutely necessary. However, they also have very high area cost because of the large number of DRAM rows that we have in today's DRAM devices. A second approach leverages the observation that an attacker can only activate a subset of the DRAM rows before DRAM cells are refreshed, and therefore they allocate one activation counter per potential aggressor row. So since these counters are still pretty accurate, they incur low performance and energy costs. However, their area costs are getting higher, especially as the RowHammer threshold reduces, because of the number of aggressor rows increases significantly with low RowHammer thresholds. And also, since these counters are allocated per specific DRAM rows, they need to store and search tags, and therefore they are implemented with content addressable memories. And a third approach allocates even less counters than one counter per DRAM row by either introducing shared counters that track multiple DRAM rows with each counter, or by introducing probabilistic preventive refreshes. And therefore, they have low area costs. However, as the RowHammer threshold decreases, they have high performance and energy costs because they have a high DRAM bandwidth consumption with their preventive actions. So ideally, we would like to achieve low energy overheads per processor chip, DRAM area overheads, and also low performance overheads. However, as you can see from this radar chart, none of the existing mitigation techniques prevents RowHammer at low area, performance, and energy costs. And our key idea is to prevent RowHammer bit flips with low cost in highly RowHammer vulnerable DRAM-based systems. To achieve this goal, we first look into different types of counters. The first one is hash-based counters that have low cost, and the second one is tag-based counters that are highly accurate. We want to get the best of both worlds, and now let me explain how these counters work. So hash-based counters map DRAM rows to an array of counters by using hash functions. So this enables two benefits. First, now we can implement these with low-cost structures because the mapping does not need any tags. And second, we can aggregate many rows activation counts together and fit all of them into fixed number of counters. And this makes it low cost. However, as you can see here, we have a limited number of counters. Therefore, some of the rows share activation counters, and an activation to one row can increase the activation counter of another DRAM row, which reduces the accuracy. And tag-based counters addresses that because each one of these counters track only one row's activation count, and they have high accuracy. So to get the best of both worlds, our key idea is to use low-cost and scalable hash-based counters to track most DRAM rows activations with low area overhead. And second, we use highly accurate tag-based counters to track only a small set of DRAM rows to achieve low performance overhead. And to this end, we propose CoMeT. CoMeT has two key structures. The first one is the counter table that maps each DRAM row to a group of low-cost hash-based counters as uniquely as possible by employing the count miscatch technique, which I will be talking about in detail in a minute. And it triggers a preventive refresh to an aggressor row's victim rows when the aggressor row's counter group reaches an activation threshold. And counter table tracks DRAM row activations at low area cost. And the second structure is the recent aggressor table that allocates highly accurate per DRAM row counters for only a small set of DRAM rows that are activated many times. And by doing so, it reduces the performance penalties and increases the tracking accuracy. Let's look at a high-level summary of how CoMeT operates. When there's an activation to row A, CoMeT first checks the counter table and gets an estimation based on the hash-based counters that it stores. And at the same time, CoMeT checks the recent aggressor table that has tag-based counters and gets an estimation when there's a tag match in the recent aggressor table. And then CoMeT compares the estimation of the activation count to a preventive refresh threshold. And that if that estimation reaches the threshold value, it preventively refreshes A's victim rows. Let's look into the counter table in more detail. The counter table employs the count miscatch technique, which is a hash-based frequent item counting technique that uses hash functions and one counter array per hash function. When we have an activation to row A, the counter table first gets the output of the hash function using the row ID as the input for the hash function and uses the output as an index to the counter array and increments that counter. When we have another activation to the same row, the counter table increments the same counter. And when we have an activation to another row, ideally the hash function results in a different index and the counter table increments a different counter. However, as we have a limited number of counters, sometimes some DRAM rows increment the same counter. And in this example, an activation to row C results in incrementing the same counter that is mapped to row A. And we call this a counter collision. Counter collisions cause overestimations. And as an example, if we were to estimate the activation count of A, we would estimate it as 3. However, the actual activation count is 2. To reduce these overestimations, the counter table implements multiple hash functions, each mapping to different counter arrays, basically creating as unique as possible counter groups per DRAM row. And the counter table increments each counter in the counter group when a DRAM row is activated. And this results in the minimum counter value being an upper bound for the actual activation count. So here we have multiple hash functions, and basically CoMeT estimates the activation count as the minimum counter value, as it is an upper bound. And in this example, this results in the estimating the activation count of A as 2 as opposed to 3, and basically the overestimation is reduced. CoMeT sets a preventive refresh threshold to timely refresh an aggressor row's victim rows to prevent bit flips. When we have an activation to row A and the counter table counters are at the threshold value, CoMeT first identifies A as an aggressor row and preventively refreshes A's victim rows. Ideally, what we would want to do here is to reset counters because the victim rows are already refreshed and we don't want to refresh them again when we have an activation. However, doing so effectively resets shared counters, and that can result in disturbing other counter groups. So if we were to estimate the activation count of row C, this would result in an estimation of 0, which is an underestimation, and this could lead to potential bit flips. To avoid that, CoMeT does not reset any counters in the counter group after preventively refreshing victim rows. And because of that, the actual activation count becomes 0. However, the counters saturate at the threshold value. And when we have another activation to row A, the estimation is still at the threshold value, which causes another preventive refresh. And this can potentially incur performance and energy overheads. However, if we knew that we already preventively refreshed A's victim rows, we could have avoided that. And the recent aggressor table does exactly that. It allocates per DRAM row counters for aggressor rows to accurately estimate their activation counts after preventive refreshes. So after identifying A as an aggressor row, CoMeT preventively refreshes A's victim rows and allocates the recent aggressor table entry and initializes the counter value as 0. And when we have another activation to the row A, this would result in a tag match in the recent aggressor table, and then CoMeT estimates the activation count as 0, which is 100% accurate because the recent aggressor table counters are not shared across different DRAM rows. And CoMeT only implements this for a small set of DRAM rows to maintain a low area cost. This was the high-level summary of how CoMeT operates. We have more operational details for CoMeT, starting from counter update policy, periodic counter reset mechanism, and recent aggressor table eviction policies, and many more details. You can check our paper for those, or I can answer your questions after the presentation. Let's move on to the evaluation methodology. We evaluate the performance and energy consumption with cycle-level simulations using RAMulator and DRAM power. These are the system configurations that we used. We compared CoMeT against 4 state-of-the-art RowHammer mitigations across many single-core and multi-core workload mixes. And you can check all that from this link. And we evaluate the area and storage overheads of mitigation techniques using cacti. And this is the area comparison. So this is the area overhead of CoMeT across different RowHammer thresholds. And as you can see, as the RowHammer threshold decreases, CoMeT's area overhead also decreases. This is because CoMeT stores fewer bits for its counters as the RowHammer threshold decreases. And this is the area overhead of graphene. And CoMeT's area overhead is significantly less than graphene's because graphene uses CAN-based and tag-based counters. And this is why it has a high area overhead. And this is the area overhead of Hydra, which is pretty similar to CoMeT's area overhead. And we conclude that CoMeT incurs significantly less area overhead than graphene and a similar area overhead to Hydra. We evaluate the average performance and DRAM energy overheads of CoMeT across single-core applications, and this is the performance results across different RowHammer thresholds compared to a system with no RowHammer mitigation. So basically, as the RowHammer threshold decreases, CoMeT incurs more preventive refreshes, and then it has a small performance overhead. And this is the normalized DRAM energy results for RowHammer for different RowHammer thresholds. And we conclude that CoMeT prevents bit flips with very small average performance and DRAM energy overheads compared to the baseline with no RowHammer mitigation. This is the performance comparison of CoMeT against 4 state-of-the-art mitigation techniques across single-core applications. And these are the performance results for RowHammer threshold of 1000. And as the RowHammer threshold decreases, the performance overhead increases for all mitigations. We have 3 key observations from this figure. The first one is that CoMeT outperforms all low area cost mitigations starting from the RowHammer threshold of 500. It incurs a small performance overhead over graphene and outperforms Hydra at all RowHammer thresholds. And these are the results for multi-core workloads, and the performance trends are similar to single-core performance trends. And here we have the DRAM energy comparison of CoMeT across single-core applications. And we make 3 key observations. The first one is that CoMeT consumes less DRAM energy than all low area cost mitigations for all RowHammer thresholds. It also incurs a small DRAM energy overhead over graphene and consumes less DRAM energy than Hydra. And multi-core energy trends are similar to single-core energy trends. We have more details in the paper, starting from security analysis of CoMeT. We show that CoMeT prevents all RowHammer bit flips for all RowHammer thresholds. We have a sensitivity analysis to configure CoMeT with each design parameter sweeping from all possible combinations, not all, but many. And we have the CoMeT's performance under adversarial workloads, comparison against throttling-based mitigation techniques, and CoMeT's performance at high RowHammer threshold values. And you can check our paper for those details. And CoMeT is open source and artifact evaluated, and you can check our source code and all scripts and all workloads from this link. And let me conclude my talk. So our goal was to prevent RowHammer bit flips with low area, performance, and energy overheads in highly RowHammer vulnerable DRAM-based systems. Our key idea is to use low-cost and scalable hash-based counters to accurately track DRAM row activations. CoMeT tracks most DRAM rows with scalable hash-based counters by employing the count sketch technique to achieve a low area cost, and tracks only a small set of DRAM rows that are activated many times with highly accurate per DRAM row activation counters to reduce the performance penalties. Our comprehensive evaluation showed that CoMeT achieves a good trade-off between area, performance, and energy cost, incurring significantly less area overhead and outperforming the state-of-the-art mitigation techniques. And CoMeT is open source. So that concludes my talk. Thank you for listening, and I'm ready for your questions.